Great to see you all after lunch. I hope you enjoyed. And we are currently continuing our Quantum Day. With that, I would honor to invite our next speaker. It's she, Professor Roni Ilan, Professor of Physics from the Tel Aviv University.
Okay, I adjusted to the proper height. Hi everyone. My name is Roni Ilan. I'm from the Condensed Matter Department here at the School of Physics at Tel Aviv University. And what I'll talk about today is topological materials and the elusive topological qubit. So if you remember, if you were here for Chaim's talk, then Chaim showed a slide where he displayed the different platforms in which we currently have operational qubits. And one of them was a topological, maybe you missed it because it had 0 operational qubits on it. And I think it was the only one that had 0 operational qubits. So my talk is going to be about that qubit. And I hope that during the talk I will be able to convince you that it is an interesting physical object. Okay, there are interesting physical problems and solutions behind it. And also that there's still hope and why it's worth pursuing that particular form of qubit, and I'll survey a little bit where we are in that pursuit. Okay, so this is the standard slide. I think basically everyone showed this is the difference between a classical bit and a quantum bit, and this is the most basic cartoon that people are showing, is one has 2 states and can be in either 1 or 0, plus or minus, on and off, but it has 2 states and you can be either here or here, and the quantum version of that is something that can be in a superposition, and what we're interested in is the coefficients there that describe or are related to the probabilities to be in each of these states. And you can go continuously depending on how you couple to the degree of freedom that represents that qubit. Okay, so we are interested in the quantum wave function. This is what psi represents, and this is the main object that we discuss when we discuss quantum mechanical systems. Okay, so this is my lame attempt at cartooning the different or some set of almost comprehensive list of the operational qubits that we now have in the world, and they are based on a variety of systems. We have superconducting qubits. There are several types of those. There are flux qubits, and phase qubits, and Cooper pair boxes, and so on. There are trapped ions. There are also systems that are based on neutral atoms. There are systems that are based on spin, which is a magnetic degree of freedom or some angular momentum of particles. There are qubits based on photons, quantum dots. It's a long list, okay? And each of these is a physical object, is a physical system that has its own sensitivity, and it has its own source, or maybe several sources, mostly several sources, of errors, okay? Things that couple to the system, that the system is sensitive to and causes errors, and basically displace the state from take away the control over the state of the system. And this can be, you know, depending on the physical object, it can be radiation, external fields, magnetic fields, electric fields. It can be differences in the materials, how we fabricate it. Fabrication is never uniform. It can be differences in size. Temperature is a main object that destroys our ability to have perfect control. Doesn't matter which system it is, temperature is generally an obstacle. Apparatuses, how we approach the system. How do we couple to the system? How do we measure? How do we read out what sorts of bath the system couples to? Okay, and this is very general. Each of these systems is more prone to one or another, but generally qubits are sensitive objects. And we are interested in the question, how do we get the perfect qubit? So we want a quantum bit that is highly immune to errors, but this is given that quantum bits live in a non-perfect environment. This is always going to be the case. Okay, so we can work very, very hard in order to clean up the environment in order to prevent couplings and to make disturbances less pronounced. But maybe we can come up with a qubit that doesn't care, okay? It just is more immune naturally, regardless of what perturbation is around. So I am a physicist, and I'm interested in the hardware, and I work at the single qubit level. I'm only interested in the basic physical unit. And when you approach a condensed matter physicist and you ask them, what system do we know that is both quantum as well as extremely robust? We generally think of one system, okay? There's one system that has a phenomenal precision in some property, and this is called a quantum Hall effect or quantum Hall system. So I'm assuming that many of you don't know this, so I'll tell you briefly what it means. This is a system in which the conductivity, this is what we measure, or resistivity, becomes extremely precise even when we change the details of the system. It's a system that's subject to magnetic field. We can change the magnetic field. We can change the temperature a little bit. We can change the shape of the system a little bit. It's a solid state system. It is big. It has 10 to the power 23 electrons in it, and it has disorder. And yet you can see, even if you don't understand exactly what's going on, that there is some feature here. In this case, is the resistivity that increases in steps. And this is a measurement. Okay, this is an experimental graph, and the precision of that steps can be 10 to the power 9 digits after the decimal point. Okay, so this is the most precise quantity that we know of, and this is in a system that's very dirty and very big. Okay, so this is a remarkable phenomenon. It's been known for several decades, and it was actually the Nobel Prize in 1985 was awarded for discovering this effect to Klaus von Klitzing. So this is a big deal, okay? It defines a measurement unit of natural constants. I'm showing them here. Okay, this is this resistivity I talked about, and here is an integer describing this. Okay, so as of now, I didn't tell you anything about qubits. I just told you something about something that is very robust in solid state. Okay, so how do we achieve this system? People know how to do this for several decades. We take electrons and we confine them to live in 2 dimensions. This is done at the interface of 2 semiconductors. Basically, the electrons are spilled into there. Okay, 10 to the power 23 electrons, or maybe a bit less because it's 2 dimension, and this is the system that we're working with. And then you cool it down to extremely low temperatures, and you put it under the influence of a very large magnetic field of the order of 10 Tesla, or maybe more. Okay, and then this is where the phenomenon is displayed. Okay, so what is the reason? First of all, let me tell you briefly what is the reason for this robust feature. So this is transport, okay? We take particles from one side of the system to the other, and we see that it's not sensitive. And the reason for this robust feature is the property of the electron energy bands, okay? It's a quantum mechanical effect. Even if you don't know what energy bands mean, I will tell you it determines how, what is the velocity of the particles basically inside the system. Okay, so this is called energy bands, and the energy bands become incredibly robust. They are characterized by what is known as a topological invariant. We use the mathematical theory of topology to describe it. This is something that I'm not getting into. But there is a characterizing integer to this system that cannot be changed by small or smooth perturbations to this system. Okay, so what is the result? The result is that the dynamic of the electrons, and there are many of them, is not influenced by small perturbations. And another way to understand it is that magnetic field completely quenches the kinetic energy. The particles in 2 dimensions here inside, they freeze, okay? They're trapped into their position. And the currents in the system flows only along the boundaries. And they flow in a chiral way. This is a system that doesn't scatter charge. Okay, so this is one of the most amazing things that we know in condensed matter called the quantum Hall effect. Okay, so now let's get more towards the qubit and how do we relate this system to topological qubits. Okay, so it turns out that if you take this system and you increase the fields more, okay, maybe 30 Tesla, and you lower the temperature a bit more, and you clean it up more, you don't clean it completely, that's not possible, but you clean it up more, these steps break and they start appearing at places where this number here is a rational number. It's not an integer. And this is called the fractional quantum Hall effect. It's still the same effect. You see that the steps are smaller than what they used to be, but they're still very precise, okay? And this is an effect that comes because of electron-electron interaction. We have 10 to the power 23 particles that have charge in the system. We quench their kinetic energy, so the kinetic energy became an energy scale that is irrelevant compared to interaction. And now these particles basically forget that they are electrons, they lose their individual identity, and they don't behave like single electrons anymore. So what does happen in the system? It turns out that in this system, if you use standard ways of measuring charge, you will see that there are particles inside the system that have a fraction of the electron charge, okay? But how is this possible? We're physicists, and we know that electrons are fundamental particles. This means that they are not composed of anything else, okay? You cannot break an electron into smaller pieces. And moreover, electrons have the smallest charge in nature. This is known. They have the smallest unit of charge. And I'm telling you that the individual particles, they have particle-like properties that live in the system, can have a fraction of the electron charge. And this is a result of electron correlations. This is what we call a many-body effect. It's a collective excitation in the system, okay? And this is possible in 2 dimensions, okay? In 2-dimensional correlated electronic systems, new particles can emerge where the charge is fractionalized, okay? This is another Nobel Prize that was given in the 1990s, both for experiment and for the theory that explained this effect due to correlations. Okay, so we see that we can fractionalize charges, but what other interesting properties can these particles have? So another interesting property that they can have is that they can have unconventional quantum statistics, okay? And for this, I need to explain to you, what does it mean to have a quantum statistics for those of you who are not physicists and don't know what it means. So nature basically has 2 types of particles, okay? Particles can be split into 2 categories, quantum categories, that determine how the wave function, which we mentioned earlier in the talk, behaves when there are many of them and they are swapped. The positions are swapped, okay? So in nature, in our 3+1 dimensional universe, 3 special coordinates in one time, we only have 2 types. They are called bosons and fermions, okay? So if we have a collective state, we have multiple particles, then the quantum mechanical wave function, when 2 of these are swapped, let's say the positions are swapped, bosons, nothing happens to the wave function, and for fermions, there is a minus sign, okay? It doesn't sound something very interesting, but this is actually the reason we have fermions is the reason why you're not falling through the chairs that you're sitting on and why atoms are stable, okay? Because electrons, for example, are fermions, okay? So quantum statistics is something that's very, very important for the behavior of quantum systems. And it turns out that in quantum Hall effect, you can have other types of statistics. Okay, so why is it that in 3 dimensions there are only 2 types of statistics? Let's look at the process of swapping 2 particles. Okay, so this is one swap. Oh, okay, and this is another one. Okay, and in 3 dimensions, 2 swaps, which are basically equivalent to taking one particle around the other, okay, is completely equivalent to doing nothing. Why? Because if you have 2 objects that are point-like in 3 dimensions, there's no such thing as one going around the other. Okay? There's no such a thing. It's meaningless. Because you can take the trajectory of this particle and very gradually shrink it to 0. You lift it out of the plane because you have 3 dimensions, and you shrink it down to 0, so 2 swaps are equivalent to nothing. So in 3 dimensions, one swap can give you a plus or a minus to the wave function, the quantum mechanical wave function. Those are all the possibilities. Okay, this is what the process looks like as a function of time. Okay, this. Okay, but if you are in 2 dimensions, this is no longer the case because I cannot make this adiabatic change to the trajectory. Okay, basically, one particle always acts as a topological defect for the trajectory of the other. There is such a thing as one going around the other, so I can't prove that there are only 2 types of statistics, and actually, this is not true anymore. So what other possibilities can we have? Okay, we can have a phase, a complex number that multiplies the wave functions as perfectly allowed. This is if the wave function is unique. There's only one quantum mechanical wave function compatible with a set of identical particles. But there is another possibility that is much more interesting than that, and this is when the wave function for the collection of particles is not unique. Namely, there are several of those. Okay? And in this case, we call the statistics non-abelian. Why? Because when we swap two particles, we are no longer multiplying the wave function by a phase. We are actually multiplying a subset of states by a unitary matrix. Okay? And unitary matrices, this is what we want when we talk about qubits, right? We want a quantum mechanical system that we do operations on, and these operations are described by unitary matrices. Okay, so non-abelian particles basically give you the opportunity to realize these kind of operations by taking the particles and moving them in real space, swapping them in real space. Okay? So this is what the process looks like as a function of time. Okay, I have a collection of these weird particles with fractional charge and weird quantum statistics. And when I do this, we call this braiding. Okay, when I braid the particles one around the other, I get unitary operators acting on a set of quantum states. Okay, and it's very difficult to do these operations by accident. Okay, if there is a finite temperature or some field that couples to the system, it's very unlikely that it will just take one particle and kick it in a circle around the other. Okay, so this is why we say that these bits, quantum bits, are protected. Okay, so these are called topological quantum bits. They are composed of a collection of several particles with non-abelian statistics. Okay, so non-abelian statistics means that operations are basically error-free, or the computation, people call it fault tolerant. Okay, we heard the combination of word fault tolerance several times in this conference. It's something that's highly desirable. Okay, and the reason it's fault tolerant is because if you look at this process, the lines, we call them world lines of these braids, they can wiggle and they can shake, but the topology of the trajectory of the particles around the other is what's important. Okay, it doesn't matter if the trajectory shakes a little bit, it just matters if this one went around that one. Okay, and this is highly immune to errors. Another interesting fact about these systems is the number of states grows exponentially. Okay, each particle like this is characterized by a number called the quantum dimension, and the size of the Hilbert space, the size of this subset of states on which we do operations, grows as this quantum dimension to the power of the number of particles. Okay, so you have the possibility of having many, many quantum states. Okay, so this is the dream. The dream is to have this subset of quantum states with a collection of particles. And this is the only thing that exists in the world, and therefore your quantum computation or your quantum bit is protected from errors. Okay, but what happens in reality? You already know a little bit about what happens in reality. In reality, we don't have a qubit like this yet. But also, if we had it, it would be living in a physical system. And that physical system would have other states that are less interesting, and they live at higher energies above that subset of states that you're interested in, and that could interfere with any process that you're doing. Okay, so this collection of states lives down here in energy, and then there is presumably some energy gap, and here there is a bunch of trivial mass of electrons and things flying around. Okay, so this energy gap here would basically put limitation on how fast you can do these operations. They have to be very, very slow, okay, if you are able to have these particles. Okay, so where are we in the quest of actually seeing or realizing these anyons, as we call them, because they're not fermions and they're not bosons. They're somewhere in between. They're called anyons. So actually, this is a problem that people have tried to tackle for a long time. Okay, I did my PhD in started it in 2006, and I started working on designing experiments. I'm a theorist, so I propose things that people maybe can do. And we started proposing ways to detect these particles, and this has been going on since then by a bunch of brave people who never gave up. And just very recently, you can see it shows a subset of papers that are important, and 2 of them came out in 2020, 1 of them came out in 2023, where this quantum Hall system, fractional quantum Hall effect, that we have observed several decades ago, actually built experiments that showed signatures of this anion statistics, okay? But only it's in abelian form, not in the non-abelian degenerate form, okay? So what people typically do is they take this 2-dimensional system and they put gates on them, and the gates define the way that the particles travel through the system. Some particles are trapped here, and then you can make particles have closed loop around the other, okay? And they do interference of these particles, and interference is the way to see phases in quantum systems. So this is how the detection works. We now have confirmation in several ways. Another way is to do scattering experiments, okay? This is an experiment that scatters. Bosons and fermions bunch or anti-bunch. When they scatter, anyons do something else. Okay, so we are there. We have detection of abelian anyons. What about non-abelian anyons? There are signatures that are consistent with non-abelian anyons. Okay, I'm happy about that, but maybe that's not yet good enough to make a qubit. It's definitely not good enough to make a qubit. What do I mean by signatures that are consistent? We know of a detection of something that's compatible with the fractional charge, the correct fractional charge of the non-abelian particle. We have compatible number of edge modes, so the currents that move on the edge can have various properties depending on which particles live inside the system. So there are several indications that some of these states here, many body states, have non-abelian excitations. But this is still not a confirmation. Okay, this is not still a direct measurement, and in particular, this is still not a qubit, because in order to make a qubit, you need to have actually 2 interferometers like this, for example. This is one way to design a qubit with non-abelian particles, and as you've seen, the previous experiments had 1. So there are also experimental milestones to meet even after we confirm the existence of the non-abelian anyons. Okay, so now, it doesn't have to be a quantum Hall system. Since this took a long time, the community was very creative in suggesting other ways to achieve non-abelian anyons, okay? And there is the engineering approach. The engineering approach says you have a system that doesn't have them, a system that doesn't have them. Let's try to put them together and see if we can make them by making various heterostructures. So some examples are taking conventional superconductors that we have and we know very well, and interfacing them with other systems that have interesting topological energy bands, like topological insulators. And then at the interface between these systems, you would trap some superconductor. This is not enough yet, because you need to put a magnetic field on the system and put vortices in the superconductor. And then presumably you have non-abelian excitations sitting at the interface here. It's a very complicated system. Okay, it's a very complicated device, and we still don't have confirmation even here. And people suggested that maybe if we put magnetism here, that would help, because it's a different type of a topological superconductor. It didn't help as well, and this system has its own problem because magnetism is non-uniform. Okay, so we try to design various things. There are other architectures that are not in 2 dimensions. If you go down 1 dimension, the system might be more simple. You take a semiconductor wire and you put it on a superconductor. This is actually the platform that Microsoft was working on for over a decade. Okay, so this system needs superconductivity induced in a semiconducting wire, and then under the application of a magnetic field, there are these end states that are trapped here. But we are in the wrong dimension in this system. Okay, this is a 1-dimensional system. Even here, we don't have conclusive evidence. But even if we did, okay, we would have to then design an architecture that takes it into 2 dimensions and allows us to braid the particles. Okay, so engineering topological qubits is very hard, and also seeing them naturally in systems requires a lot of extreme conditions and resources. Okay, there are particle challenges. You either need high magnetic fields, extremely low temperatures, complex heterostructures. You need to couple to superconductors. You're in the wrong dimension, okay, 1 instead of 2. But there are also conceptual challenges that we need to deal with, and this is disentangling effects that are related to the actual anion statistics and the particles that we're interested in, from more mundane effects and electronic excitations. and we need to find ways to make competing mechanisms coexist. For example, superconductivity and magnetism, it doesn't like to live together. Okay, magnetic fields and superconductors are not good friends because superconductivity is suppressed in the presence of magnetic fields. Okay, so it all sounds very depressing, right? And what can I say that's hopeful for the future? Now you actually understand a little bit about why there are 0 operational qubits, but you also understand that if we are able to make that, if we're able to have that milestone of that first qubit, then this offers a huge advantage. Okay, so what turns out to be the perfect qubit is now an underdog in terms of realizations. What can we promise for the future? Okay, can we get some of these effects for free? For example, not needing external magnetic field. And one of the key things that happened very recently is that we discovered that similar effects can happen in layered materials. Okay, so this is something that happened recently. 2018 was a good year when quantum materials made a huge quantum leap and graphene became superconducting. So I'm sure you all saw graphene, so a single layer of carbon atoms, and it turns out that when you put them together, one on top of the other, and you rotate them by something like 1 degree, this creates an astonishing effect where the energy bands of the electrons become completely flat. So what does it mean that an energy band of electrons is flat? It means that the kinetic energy is quenched. This is what we got with a magnetic field before. Now it happens because of the geometry of the system. So this brings out correlation effects, and people are now able to stack these one-dimensional systems that basically do whatever they want to the electron bands and bring out these many-body effects. Okay, so this is what's going on now. In these systems, it turns out that these many-body effects related to anyons are now starting to be observed. Okay, this is the fractional quantum Hall effect, or what we call fractional Chern insulator. Okay, it's a different system. It's not under the influence of an external magnetic field. This is a system in which magnetism arises intrinsically. Okay, so that's some improvement. As you can see, the steps here are not so nice, like in the quantum Hall effect, but this is only the beginning. And now this is a huge field of research where we start looking for anion signatures, and people already start to see signatures that are consistent. So far, 1 billion anions, but we are hopeful that also non-abelians are going to come up next. And with that, I want to conclude. So we have new developments, both in the fractional quantum Hall effect, that are very promising. Okay, new experiments that took decades, but are now working. We have new quantum leaps in material science that basically unlock the possibility of creating new and very highly tunable systems, and then states that support anion excitations can emerge. And I, as a theorist, am very happy because I can go back and look at these topological objects and see, you know, if you have new types of quantum statistics, this means that you have very fundamental physics questions to ask even before you approach the qubit. But on the engineering levels, we have new possibilities for engineering both particle paths and traps. And so I'm leaving you with something optimistic, and I thank you for your attention.